Hey, everybody. So in this lecture, I'm going to talk a little bit about using statistical hypothesis testing to compare, say, the mean of some data to a specific value that you're interested in. So that's kind of a continuation of some of the material that we covered in the lecture, as well as using statistical hypothesis testing to compare two different means, as well as two different proportions of samples that maybe represent events. So anyway, I know that may be a little bit vague, but we'll get into it, and hopefully it'll be clear as we go. So let me go ahead and get the lecture started here and select the right window. And hopefully we're on our way here. Okay. All right, so we are talking about statistical inference in general, and that is basically using measurements and some statistical magic to infer information about the population from which those samples are drawn. And we talked about point estimation. As I mentioned in the beginning, we're really talking about hypothesis testing in this lecture. And in one of the earlier recorded videos, I talked about some of the foundational information that we need, foundational theory, to carry out these statistical hypothesis tests. But basically, just real quickly, the idea was that you have this idea that means of samples. So say we go down to the beach and we collect a series of samples. We measure the total coliform concentration in the samples. Those are essentially realizations of a random variable, which is indicated here by the uppercase xi. And then we can derive from that random variable a new random variable, which is essentially the sample mean, indicated by uppercase x bar here, as essentially the sum over all of those random variables representing the samples divided by the number of samples that we've collected. And of course, we can talk about a realization. And if we're talking about a realization of this random variable for the mean, that would be the lowercase x bar. And of course, that would just be the standard way of calculating the mean that you probably learned in high school. Likewise, one could calculate from that set of realizations a variance of the data, which is essentially just a measure of the spread of the data around the mean. And it too is going to be a random variable because every time we go out and collect n samples, we're going to get a different variance. And so it's going to be distributed in some way. And that would be the same for the mean. It's a random variable because if we went out and collected another n samples, there would be a different set of realizations. And we would also then calculate a different mean. And so the sample mean in this case is also going to be distributed in some way. One of the things we showed is that the expected value of that random variable for the sample mean is actually equal to the population mean. And so that means that this formula here is an unbiased estimate of the population mean. We also showed that the estimated value of the variance, the sample variance, is going to be the population variance. And so this formula for s squared, including this n-1 term in the denominator, is essentially an unbiased estimator of the population variance. We furthermore dug into the distributions of the sample mean and the sample variance a bit more. In the event where we know the population variance, so there's no real reason to calculate the sample variance, we learned that we can sort of represent the sample mean as a normal distribution, which is centered around the population mean. So it has the normal distribution has a mean equal to the population mean. And then it has a standard deviation equal to the population standard deviation divided by square root of the number of samples that we collected. And it's interesting to note that this quantity here, which we've talked a little bit about, but we haven't really focused on, sigma over square root n, is known as the standard error. And so if you see that in a document or some literature, that's what it's referring to. Sigma over square root n is the standard error. And obviously, the standard error is going to decline as we increase the number of samples that we're analyzing for a fixed population standard deviation. Because the sample mean is normally distributed, as with any normally distributed variable, we can construct a standard normal variate from that sample mean, which is going to be distributed according to the standard normal distribution, which of course has a mean of 0 and a unit standard deviation. We do that by just simply subtracting the population mean and then dividing by that standard error, and that's going to give us the standard normal distribution. So this z-bar quantity here is distributed as a standard normal when we know the population variance. If we don't know the population variance, then we have to worry about how the population variance itself is distributed, because it's going to be a random variable, remember. And what we found from that previous lecture was that when we normalize the sample variance by the population variance, it is distributed according to the chi-squared distribution, where this n-1, the number of samples minus 1, is a so-called degrees of freedom f. And I should point out that the chi-square distribution depends only on, the only parameter value is that degrees of freedom f. Likewise, the sample mean with unknown population variance can be represented by the t statistic. And all we've done is taken the z statistic here, and we've substituted for the population variance, which we don't know, the sample variance, which we can calculate. When we do that, we change the distribution. This t distribution, or this t statistics, will not be distributed the same as the z-bar statistic, because we've now replaced a known quantity for something that is itself distributed in some way. And in fact, we showed that this t statistic follows what's called the student t distribution, which is given here. This is the PDF for the student t distribution. And again, it just depends on one parameter value, which is the degree of freedom defined in exactly the same way as above. That is, f is equal to n-1. So that's kind of the foundational material. And then we started talking about this example in class. I want to go quickly through the portion that we talked about of the example, and then kind of elaborate on a little bit. The first part, basically, we are assuming that we know the population variance. In the second part, we acknowledge that we don't know the population variance, and so we have to substitute the sample variance. So that's kind of the big picture here. So it's example 6.3 in the textbook, and the problem statement looks like this. Suppose the specification for the yield strength of rebars required a mean value of 38 pounds per square inch. It is therefore essential that the population of rebars to be used in the construction of a reinforced concrete structure has the required mean strength. From the rebars delivered to the construction site by the supplier, the engineer, that would be you, ordered that a sample of 25 rebars be randomly selected and tested for yield strengths. The sample mean from the 25 tests turned out to be 37.5 pounds per square inch. It is known that the standard deviation of rebar strength from the supplier, that suggests the population variance, or the population standard deviation, is going to be 3.0 psi. Should this lot be rejected? Now, that's a very interesting question, because before taking this class, you probably would have said, yeah, obviously, the sort of required value is 38, and we got 37.5, so that means that the rebars are not up to snuff and they should be rejected. But the thing is, now we understand, having taken stats, that when we take that mean of the yield strength for the 25 rebars, in fact, that's a random variable. So it's going to exhibit natural fluctuations that are independent of the yield strength of the population from which the samples are drawn. So the population could have a yield strength of greater than 38 psi, but the set of 25 samples that we drew from that population could give us a yield strength less than 38 psi. So to really evaluate the answer to this question, we basically have to take into account the fact that there's going to be natural variability, which may give us a number lower than 38, but it doesn't actually reflect a population which is lower than 38. So we really have to use statistical hypothesis testing to answer this question. And so step one of that process would involve defining the null and alternative hypotheses. And so in this case, the null hypothesis, H0, is going to be that the population mean of the yield strength for rebars is greater than or equal to 38. You know, you can basically say this is equal to 38, but the reason that we're including the greater than here is that, look, I mean, if the population yield strength is greater than 38 psi, we don't really care. That means that the rebar is strong enough. And so we're not going to reject the lot. The real issue here is whether we should reject the lot or not. So we're really interested in knowing, for the null hypothesis, is the mu greater than or equal to 38, in which case we're not going to reject the lot, or does the alternative hypothesis apply, which is that the mu is less than 38, in which case we have to reject the lot. So in this sense, this is a, one-sided test, because we're only really, for the alternative hypothesis, we're only really interested in rejecting if the population mean is less than that 38 standard. Okay, so we were given the population variance or population standard deviation. And so for this particular hypothesis test, in step 2, we're going to choose for the test statistic that z-score, which is just a standard normal vary constructed from the sample mean minus, now we're going to substitute for the population mean the specific value mu naught that we're interested in comparing to. So really what we're saying here is that we're going to assume that the population is in fact, does have that value of 38. And then so basically that the null hypothesis is true. And then we're going to look at how the z statistic that's constructed from this difference between the sample mean and that target mu naught is distributed as a function of z. And we know in particular that it's going to be distributed as a standard normal variate. That's our foundational theory. So we're good to go. Step 3, we need to evaluate that test statistic. So we go ahead and plug our numbers in. So we've got 37.5 for the observed mean. Again, 38 is the population mean that we're going to hope that we have. So that's kind of our null hypothesis. We were told that the standard deviation of the population is 3 psi. And we had 25 samples, so we plug in 25 for n. And when we calculate that z statistic, it works out to minus 0.833. So the step 4 is that we have to specify the level of significance, which really boils down to specifying the probability that we are willing to live with of making or committing a type 1 error. And remember, the type 1 error is the case where the null hypothesis is true, but because of random variability in the z-bar, we end up rejecting that null hypothesis. So we essentially have created a type 1 error. And I should just say that in this case, we're going to go ahead and choose the alpha equal to 0.05 as the level of significance. That's a really typical value. If you wanted to be more conservative, you could bring that down to alpha equal to 0.01. And so basically what we're saying with that z-bar statistic, remember, it's centered around the population mean equal to 38. So if z-bar was equal to 0, that would mean that our sample mean was exactly equal to the 38 psi. That is our standard. And we're really only interested in rejecting the null hypothesis or rejecting the lot if that 37.5 is significantly below the, is significantly smaller, I could say it that way, than the 38 target. And what does significantly smaller means? Well, it basically is defined by that threshold that we set of alpha equal to 0.05. And so what we're saying is that this probability distribution, remember, represents the value or the probability density associated with z-bar, given that the null hypothesis is true. So you can see most of the probability is kind of in this range here, but then of course we have some probability out in the tail where we would actually get a z-bar out here, even though the null hypothesis is true. Well, we basically set a threshold and say, okay, we're willing to accept the possibility that we're going to be wrong. We're going to reject the null hypothesis incorrectly 5% of the time, which means that we look for the critical z value, which gives us 5% probability in this left tail. So if z bar basically crosses into this dark blue area, we're then going to reject the null hypothesis and then not reject the alternative hypothesis that the population mean is less than 38. So hopefully that makes sense. The only other thing is we need to then calculate what the critical value of z would be at that 5% threshold. And to do that, we remember we're working with the standard normal distribution here. So we essentially take the inverse of the CDF for the standard normal and operate it on the alpha equal to 0.05. So that would correspond to the critical value here. Remember that our probability charts are not tabulated for the left side of the probability distribution, only positive values of the standard normal variate. And so we apply the transformation that basically says this thing can be set equal to minus the inverse of the CDF operated on 1 minus that alpha. So it's going to be 0.95. And if we go to our charts, so we come down here and we look for 0.95, we find that the critical value for z is about 1.65. And in fact, if you bring it out to 4 significant digits, it's minus 1.645. But anyway, so that would be how we calculate that critical value of z given a statistical threshold of 5%. And so remember, our measured z statistic is minus 0.833. Our critical value is minus 1.65. So basically, when we plot those together, we see that our measured value falls within the region where we were not going to reject the null hypothesis. It isn't in this blue region here. And so therefore, we conclude that the alternative hypothesis that the population mean is less than 38 can be rejected at the 5% significance level. And so given that, we would basically say, as an engineer, that the rebar satisfies the required strength, even though the actual measurement that came back was less than 38. So hopefully the distinction between sort of like in the old days, you just like look at two numbers and say, oh yeah, they're different or they're the same. Here when we're doing statistical hypothesis testing, we're a lot more nuanced about exactly what that means. All right, so I pretty much went through that problem the last time. Now, in the lecture last week. Now I want to elaborate on that example a little bit by saying, okay, what if we didn't know the population variance? That's a very common situation. And so we're given the sample variance. Well, actually, this is an error. That should be sample standard deviation. So we're given the sample standard deviation of 3.6 PSI. So we basically calculated from the 25 rebar samples sample variance of 3.6, and we're going to have to use that in place of the population variance or standard deviation because we haven't been given it. And so we're still asked, is the shipment of rebars acceptable? And so in this case, because we don't know the population variance or standard deviation, we have to use the t statistic. And so remember, it's basically the same as before, except we're substituting the sample standard deviation for the population standard deviation. And again, we're basically just taking the deviation of our sample mean from the target mean, that mu naught, which in this case is 38, and we're normalizing it by the standard error given this sample variance. And when we calculate that out, it works out to minus 0.694. Now we have to determine what the critical value of the t statistic would be for a statistical threshold of, again, 5% or 0.05. The way we do that is we take the inverse of the CDF for the t distribution and basically operate it on 0.05 or 5%. And if you look at the t distribution, it's symmetrical about 0. So it's kind of like the standard normal distribution in that way. And in fact, actually, in the limit of infinite degrees of freedom, so we collected infinite number of samples, the t distribution would become exactly equal to the standard normal distribution, which is indicated by that top curve there. But anyway, the bottom line is that the most of the tables for the t distribution only, because this is a symmetrical distribution, only plot the cumulative distribution function for positive values of t. So if you want to get a value for down here, you basically have to use the same transformation that we use for the standard normal. Let me elaborate. So in this case, we want to know the critical t-statistic value for alpha equal to 0.05, which is going to be the inverse of that CDF for the student t-distribution acted on or evaluated at 0.05, which is the same, just like with the standard normal, we can make a transform. So that's going to be equal to, because of the symmetry of the t-distribution, minus that inverse of the CDF acting on 1 minus alpha, which in this case is 0.95. And then we just need to go look up what that corresponds to. So in this case, we're at alpha 0.05. So that's going to make a p, as defined here, of 0.95. So we're in this column. And then we just go down and find our appropriate degrees of freedom, or F. So in this case, we had 25 samples. So the degrees of freedom were 25 minus 1, or 24. So we come down and we see for 24 that our appropriate value for the critical t is 1.71. And so since we had a minus sign here, we have the result that the critical t value for a statistical threshold of 5% is minus 1.71. And if we graph it out, then basically what we're looking at is as follows. So the horizontal axis here is our t statistic. And our calculated or measured value is coming in at about minus 0.694. The critical value for a 5% statistical threshold is minus 1.71. And since the measured t falls to the right of that critical value, that means we cannot reject the null hypothesis, which in this case basically means that we can't say that the mean that they collected of was it 37.5 is statistically different from 38, and therefore we do not reject the rebars. They essentially satisfy the required strength. All right, so that's the case. This is essentially a set of examples where we're looking at comparing the mean of some sample data to a very specific value, in that case, a threshold of 38 psi. Oftentimes, we're called upon to tackle a slightly different kind of problem, which is where we have two different means that we've calculated from two different sets of samples, and we're asked to determine, are those means essentially sampled from the same population mean, or are they sampled from different populations? In other words, are they statistically the same, or are they statistically different? And so in this case, the null hypothesis, while that was the previous situation, we basically would say, okay, is the population mean equal to a specific value? That was our null. The alternative was that the population mean was not equal to a specific value. So that's what we've looked at so far. In this case, what we're basically doing is saying for the null hypothesis, is one population mean equal to another population mean, or the alternative, are those two population means different? And let me give you kind of a graphical, or walk you through a graphical interpretation of what I'm talking about. So basically, imagine a situation where your population in the wild, there's really one population in the wild that you were sampling from, and you didn't necessarily know that there was only one population, but anyway, that was the case. And it was characterized by a unique population mean, mu. And so we go out and we collect a bunch of observations, say observations A, which would be a series of measurements. And maybe we have n sub a of those measurements. And so each of these little x values would be a realization then of the random variable for the population in the wild that we're sampling. We might then take all of those observations and calculate a sample mean like we would in high school. We just divide by the number of samples associated with those observations and sum up overall the observation values. And then we might go out and either choose a different location where we were sampling, or maybe a different lot of items that we were sampling, or maybe it was a different time in the same location. Anyway, we go out and we collect some new observations, which we're going to call observations B. And so those are a series of observations. Maybe we have n sub b total of these observations, and we could compute a mean from these sort of b observations as well. And so then the question is, from a statistical perspective, because these realizations are obviously going to be different than these realizations from observations A and B are going to be different, our corresponding sample means for A and B are going to be different too. And so all you don't know that you're sampling from a single population necessarily. All you know is you went out and sampled twice and you got two different means, and you want to figure out, based on statistical hypothesis testing, whether these two means were from the same population or from a different population. So in this case, really, the reality is that the null hypothesis applies. That is, the population mean for this set of observations is equal to the population mean for this set of observations, which is just equal to the single population mean for that wild population. Alternatively, it could have been the case, again, we wouldn't necessarily know unless we were doing statistical hypothesis testing, that there's two populations out there that we were sampling. Maybe if we were looking at two different lots of items, there were two different people on shift when they built them, and so one person does a really great job building them, and another one does a really lousy job building them. So they're really quite different in terms of their mean properties, right? So anyway, whatever the case, we've got two populations now, a population A and a population B with their own unique population means. And then we go and we collect some observations on population A. And again, we calculate a mean for that. And we go out and collect more observations for population B, and we calculate a mean for that. Obviously, these means are going to be different. And then the question is that difference because of just random variability associated with sampling the same population, or are they different because they actually came from a different population? And in this case, again, we wouldn't necessarily know that because we're not God or some higher authority, right? So we can't see. All we can see are the observations that we collected. But in this particular scenario, it would actually be the alternative hypothesis, which which essentially applies in the real world. That is that the population mean of A is not equal to the population mean of B. So this is the point, really, that we see observations and we can calculate statistics and means and standard deviations and so forth. But we'd like to infer from that information whether this is the scenario that applies, that is, we have a single population we're sampling, or this scenario applies, we have two populations that we're sampling, and they're distinct in terms of their population means. Okay, so the tools that we use to essentially get at which of those two options apply are going to be, well, I'm going to outline them now. I'm not actually going to derive them. I'm just going to use them because we don't have time. The class is kind of over. So we're just going to sort of go straight to the answer. And basically, the tool that you use for determining whether two sample means are essentially the same, or if you're going to compare them, it depends on whether the standard deviations of those two sets of samples are similar or not. And by similar, I mean very specifically that neither is more than twice of the other. So this would be the case where the standard deviations are similar. In that case, of course, you calculate the sample means in the normal way for population A and B, and you calculate the variance for those two data sets in the normal way. And then you could calculate, or you should calculate, what's called a pooled variance, which is just a sort of weighting of the variance for A and B by the number of samples that are being collected. And once you calculated that pooled variance, basically then you can write out a t-statistic for evaluating or hypothesis testing about those two means. And in this case, the t-statistic is going to be the difference between the two sample means divided by the the square root of the pooled variance, or the pooled standard deviation, times the square root of 1 over the number of samples for A plus 1 over the number of samples for B. And the point is that this t-statistic is going to be distributed, again, that's what that squiggly sign means, according to the student t distribution with degrees of freedom equal to NA plus MB minus 2. Okay, and so basically, you proceed in the normal way. You take your measurements of A and B, compute means, compute the pooled variance, determine what your measured t-statistic value is, and then depending on the statistical significance you want to apply, you would then calculate a corresponding critical t-value, and then you would just compare your measured t to that critical value. And because the null hypothesis is that there's no difference between the means, that is essentially the null hypothesis is that these are actually essentially statistically speaking equal to zero, that would imply that if your measured t is greater than the critical threshold t, then you would reject the null. Or if your measured t was less than the critical threshold, minus the critical threshold on the left tail, you would reject the null hypothesis. But otherwise, you would reject the alternative hypothesis. So anyway, it's just basically the application of the same ideas that we've covered earlier in this lecture. So you use a slightly different set of tools if it turns out your standard deviations are not similar between the two groups. So in that case, you again calculate the mean and variances in the normal way, but you don't have to calculate a pooled variance. In this case, you just write out the t-statistic, again, in terms of the difference between the sample means, and then the sample variance for A and B directly, which is assumed to be, again, distributed according to the student t-distribution with a degree of freedom f, which is given by this complicated formula here. So it's a little complicated, but it's just some computation because you know all of these quantities, right? You know the variance of A and the variance of B. You know the number of samples for A and B, so it's straightforward to compute this degrees of freedom. I'm not going to go through any examples comparing means because I think you by now can probably do that for yourself. And in fact, you probably will need to do that for yourself for the project, the TC measurements at Huntington Beach. Let me give you a specific example of why you might want to do that. I asked you to determine the mean of total coliform for all the north stations and then compare that to the mean of total coliform for all the south stations. If you claim that those two are different, you better back it up with one of those statistical tests, because otherwise you would be violating a fundamental assumption of statistics, which is comparing numbers without doing the appropriate statistical hypothesis testing. I want to focus on another really cool statistical hypothesis test that we can perform when we're comparing two proportions. And remember what a proportion is. So in this case, let me see if I can go to, yeah, so this is kind of the setup. In this case, you have essentially a sequence of events, right? So let me elaborate. For the project at Huntington Beach, every time you collect a sample and you measure the total coliform concentration in that sample, you could call an event a situation where that TC concentration is greater than some threshold, say 1,000. So every time a sample has a TC concentration greater than 1,000, you say, ooh, that's an event, you know, because it might constitute a violation of a water quality criteria. Or the sample may have a concentration less than 1,000, which would constitute a non-event. So essentially, each sample is either an event or a non-event. And you can imagine that this is like a Bernoulli trial, right? So each sample has a binary outcome, which we can represent with either a 1 or a 0. So in particular, let's denote an event as that random variable equal to 1. So that would be the ith realization of the random variable x is going to be equal to 1. And a non-event essentially denoted by the ith realization of that random variable equal to 0. And so in the example presented just now, these events would be water samples with TC concentrations greater than 1,000. So we denote that sample with xi equal to 1, whereas non-events are water samples with a TC concentration less than 1,000, which we would denote as an xi equal to 0. The key thing is that we showed earlier that the maximum likelihood estimate for the probability of an event occurring in any one trial, assuming that the binomial theorem applies, is going to be given as follows. So p hat, which is essentially the proportion of events to the total number of trials, is going to be 1 over the number of trials, or number of samples, say, times the sum of that random variable xi over all samples. Now, you may look at this and go, wait a minute, you're pulling my leg here, because look, I mean, this is the mean, right? It looks exactly like the mean that we were just talking about. If you go back, I mean, it looks exactly like that, right? Looks like I'm trying to pull one over on you. But look, it's a bit different, because in the previous case, xi, what did it represent? It represented some finite value, right? It was like 38 psi or 25 psi, depending on the realization. You could have a whole series of like numbers, which were essentially real numbers. And then when you sum them up and you divide by the number of samples, you get on the left-hand side new real number, which represented the central tendency of the data set. Here it's a bit different, because Siri's trying to help me here. It's a bit different because all the xi's in this example are essentially either 0 or 1.
For series of like numbers of which were essentially real numbers, and then when you send me to divide by the number of samples, you get on the side of new real number.
Oh my God, Siri is so funny. I need to hide her somewhere, like bury her. I don't know, am I a murderer if I bury Siri? Anyway, so what I was saying is that in this particular case, all of the xi's are either 0s or 1s. And so when I sum up over them, basically I'm going to, because a 1 was an event and a 0 was a non-event, if I sum up over all of those xi's, I'm just going to find out the total number of events that I had in those n trials. So it's really the proportion of samples. This p hat represents the proportion of samples or trials that had events. So it is actually quite a bit different than the mean that we were talking about earlier. And the other thing that's interesting to note is that because this is a sum over a series of independent random variables, that we would expect that p hat to eventually approach a normal distribution by the central limit theorem, even if the realizations of the event or non-event as determined by the xi were not normally distributed. We're not actually going to derive the hypothesis testing formulas we're going to use, but I can just tell you that they rely on this concept that p hat is normally distributed. Okay, so to kind of basically apply the same concepts we described earlier for comparing two means to comparing two proportions, let me kind of just run through this graphically again. So now we're not talking about means of the population in the wild. We're talking about the fraction of that population which sort of has that event criteria. So maybe out in the wild, there's a population which a fraction of that population is going to have TC concentrations greater than 1,000. And just as before, we're going to collect a series of observations and determine from each of those observations whether we have an event or not. So this is a series of 1s and 0s. We've got n sub a of them for our observations A. And then we calculate from those 1s and 0s essentially the proportion of the samples which have events, denoted here as p hat because it's the estimate of p sub a, and we're just basically summing up again over all of those 1s and 0s and dividing by the number of samples we have. Likewise, we could go back out and sample again. Basically, we get another set of events or non-events, again, another sequence of 1s and 0s, and we compute a new proportion p sub b hat. So then the question becomes, is the difference between the p sub b hat and the p sub a hat, and of course there will be differences in those two numbers, are those differences statistically significant in the sense that they suggest that we're sampling two different populations, or are they just sort of random variation and we're actually sampling the same population? Well, in this case, of course, we wouldn't know that, but being all seeing and all powerful, we now know that actually we were sampling the same population. And so in this case, the null hypothesis would apply, that basically the population proportion would be the same for A and B because it's just equal to P. On the other hand, we could have a situation where there are actually two different populations with two different proportions of events for A and B respectively. And then when we went out and we collected observations and calculated from that, or estimated from that, a proportion of the samples with events in A and B, the difference between these two, again, we would be faced with the question, is it random variation, or is it actually reflecting a difference in the parent populations? And in this particular case, because we now know all, we know that in this particular case, the differences are actually real. They're statistically real because they reflect sampling from two different populations with two different proportions, which are not the same. And so in this case, the reality is that the alternative hypothesis applies, that is, PA is not equal to PB. And so basically the hypothesis testing for proportions is, when you're comparing two proportions, is just trying to distinguish between these two competing hypotheses. Another way to say it is that we're trying to infer from our data which of these two scenarios is most likely to apply. Okay, so how do we do this in practice? We can rearrange our null hypothesis to just be PA minus PB equals 0. You can see that's the same as saying that PA is equal to PB. And the alternative hypothesis is that this difference is not equal to 0. And I didn't derive this, but basically what we find, if you follow through with the logic, is that the quantity Z here, which represents the difference in the measured proportions, divided by this sort of weighted proportion, which is just a weighting of the two proportions A and B by their respective sample numbers, times whenever the number of samples in A and whenever the number of samples in B. When we compute this Z statistic, it turns out is distributed according to the standard normal distribution. And so that means that we can basically define a region of rejection. And if we think about it, so this is a Z statistic for the null hypothesis essentially being true, if you think about it that way. So if the null hypothesis is true, we would expect Z to take on a range of values consistent with the standard normal distribution. I guess that's one way to argue it. And so basically, we're going to reject the null hypothesis using a two-tailed test, because we're setting it equal to 0 here instead of just looking at one side. And that means that we're going to establish a probability threshold, or a statistical threshold, alpha. And remember, that's the probability that we're willing to accept of falsely rejecting the null hypothesis, or a type 1 error. And because it's a two-tailed test, that is, the score Z here could either be too big, and so we would reject the null hypothesis that these two proportions were equal, or it could be too small, and we would reject the null hypothesis that these two proportions are equal. And because of that, we have to divide that alpha in half, and basically assign half to the right tail and assign half to the left tail. And to estimate the critical Z value associated with those two tails, basically we just take the inverse of the CDF for the standard normal and apply it to 1 minus alpha over 2. We include the 1 minus here again just because our probability tables don't tabulate negative values of the Z-score. And so if alpha equals to 0.05, then really what we're looking for is the inverse CDF of 0.975 for the standard normal. And so we just look for 0.975, which comes in around right here. So it looks like our critical Z value is going to be plus or minus 1.96. Oops, let me go back. Yeah, and so plus or minus 1.96 is our critical Z value. All right, so let's go ahead and apply this to a problem that we've seen before, and some of you are doing similar kinds of examples like this in your own project. So I remember I had collected or analyzed all of the data that was collected at station 0 over 3 years for one of your groups. And that that particular station for those 3 years, at that particular station over those 3 years, there were 442 samples collected and measured for total coliform, or TC. So one of the calculations that we did was we looked at the proportion of those samples that had a TC concentration greater than 1,000. So that's the p hat TC greater than 1,000. I'm going to denote that as p hat sub a here. And when we worked it out, basically about 10% of the samples collected at this station for those 3 years had a TC concentration greater than 1,000. So about 44 or so of those samples had the TC concentration greater than 1,000. We could then calculate a corresponding variance for that proportion using the formula that we described previously. So we just basically take the proportion for A, let's call it probability of TC being greater than 1,000. It's the approximation of that, times 1 minus that probability divided by the number of samples. And when we calculate that out, it's 2.04 times 10 to the minus 4. Okay, so that's our variance, and that's our estimate for the essentially sample probability that TC is going to be greater than 1,000. And then I was asking another question. I said, so what happens if we recalculate that proportion or probability conditioned on salinity being less than 30? And the logic here is that the Santa Ana River, so the station 0 is right at the Santa Ana River outlet, right? And the Santa Ana River outlet, most of the year, it's actually not a river at all. There's hardly any water or any fresh water that comes out of it at all. But during winter, during storms, there's a lot of fresh water that comes out, which is usually highly polluted because it's coming from the landscape. By fresh here, I just mean low salinity. I don't mean clean. You wouldn't want to drink it. So the idea or the theory that I wanted to kind of test was the concept that if you had that sort of nasty fresh water, that is that nasty low salinity water with high TC concentrations mixing into the ocean, when you collected a sample from the ocean then along the shore, that you would see that samples which had low salinity would also tend to have high TC concentrations. So that was kind of my theory that I wanted to test. And so to test the theory, I basically computed the proportion of the samples that had salinity less than 30 that had a TC greater than 1,000. So that's a conditional probability. And the way that you may remember, the way that we calculated that was we used our set theory result. We just said that that's going to be equal to the probability that TC is both greater than 1,000 and salinity is less than 30. So it's essentially intersection of those two events divided by the probability that salinity is less than 30. So we're conditioning the probability that TC is greater than 1,000 on the probability that salinity is less than 30. And I'm not sure why I use the notation here. It's a little confusing because that looks like an intersection instead of a conditional. But anyway, you get the idea. And lo and behold, when I calculated that number, the probability that you're going to get TC greater than 1,000 when the sample has less than 30 salinity is much higher. It's 0.72 compared to 0.1. However, only 11 samples had those two conditions, that is TC greater than 1,000 and salinity less than 30. So it was a pretty small number that I was calculating that proportion from. And actually, I think the number here, the number of samples, this would be actually the number of samples that had salinity less than 30. So it was the fraction of that is also had TC concentrations greater than 1,000, 0.72. So I misspoke a moment ago. This number here is just the number of samples out of the 442 that had a salinity less than 30. So anyway, that's the probability. And so it looks like it's kind of consistent with my theory that when a sample has low salinity, it has a much higher probability of having high TC concentrations, consistent with that idea that the high TC are coming into the ocean with low salinity water. And I can calculate a variance corresponding to that using my formula, and that works out to 0.0183. And so now the question is, are these two numbers actually different from a statistical perspective? we have a much smaller n value here than we do here. So it's possible that this just is a very low precision number. We don't have very much control over how accurate it is because we have such a small number of samples that had a salinity less than 30. So it isn't at all obvious that this number and this number are just not random variations related to sample size. So the way that we go about hypothesis testing to determine if these are actually statistically different numbers is we form, again, our null hypothesis that they're essentially equal proportions. Probability A is equal to probability B. And our alternative hypothesis that those two proportions are not equal. And we first calculate that weighted probability from the formula that we described on the last page. That works out to 0.115. We substitute it into that Z formula with also the PA and PB sample probabilities, and it works out to minus 6.37. And then, of course, we need to compare that to our critical value of ZC, which you may remember was minus 1.96 on the left if we assumed a two-tailed problem and also alpha probability of type 1 error of 5%. And so basically, because our measured Z value is far left of the critical value, it's deeply into the tail, we're going to reject the null hypothesis and basically conclude that here's exactly what I wanted to say. So the two probabilities of TC greater than 1,000 are statistically different. That is, they are not drawn from the same population at a significance level of 0.05. So we might have gotten a different answer if we'd chosen a different significance level. So we always have to report the significance level at which we're doing the comparison in the statistical hypothesis testing. So the net result is that this result supports the theory that if the salinity is low, the TC is indeed going to be higher in the samples from Huntington Beach. And so coming back to our original sort of diagram, that would suggest that we can reject the null hypothesis, which means we cannot reject the alternative hypothesis. And so at a statistical significance of 5%, we would say that those two probabilities are indeed different, or two proportions are indeed different. Okay, so that's the end of my presentation. And actually, it's also the end of these online videos because it's the end of the class. So thank you so much for taking the class and suffering through all of the statistics and probability theory that we learned this quarter. It's been super fun. I've had a great time, and I've enjoyed having you in the class too. So with that, good luck on the final. And maybe as Ed Murrow would have said, what did he say? He said, good night and good luck. Okay.